Oh, hi there. I heard we're doing some office hours today. Has anyone got some questions? What are people thinking? Well, hey there, Campbell. Looks like Mary has some questions. The cops, they've got questions. The Batman, he's got questions. Gordon's got questions. The Stat 201 students have questions. All the 201 students. The 320 students have questions. The 474 students have questions. What questions are there? Looks like 320 to start. Where is Harvey Dent? We are tonight's entertainment. Just one question. Where's Harvey? Do you know where he's at? Do you know? Do you know? Do you know where Harvey Dent is at? Hey, Brian, I have a question for 320, 2E, and 2F. Got some real scars here. Got some scars on face. 320, 2E, and 2F. What are those questions? Say, let me get this pulled up right here. Turn up this volume a little bit more so I can hear myself. There we go. Need to like the full camera. Grab the camera in. So how's everyone doing? It's Halloween, or it will be Halloween. It's Halloween in the future. We're always talking in the future. Future stuff. Let me get the question 2's up right here. Everyone doing well? Let me close down this. Is Mubot awake? Mubot, are you awake? Mubot is awake. Mubot is here in the chat with us. Mubot is here. We're going to get the homework packet pulled up. Homework packet. Canvas has given a bunch of random errors lately. Here we go. There's quotes I'll say and here we go sometimes randomly. I saw Joaquin Phoenix Joker. It was good. Good job, Joaquin Phoenix. Excellent movie, but it's no Dark Knight. Sorry, the Joker was great. Excellent movie. Astounding performance. Not the Dark Knight. I mean, only the Dark Knight is the Dark Knight, but it was good. Joker's great. Joaquin Phoenix and all the leads in that, amazing job, but only Dark Knight is Dark Knight. So let's do this. Let's hop over here to Mary's question. Mary had a question. Let's do it. Okay, so we have right here question 2E and 2F. Okay, so we're using a model right here on the stocks, and we're doing 2E and 2F. Good, great questions, Mary. Let's talk about these. So we're going to grab these right here. And let's talk about these two questions. We're going to bring it over to Word. And here we go. So what is the deal? What's the deal? I'm Jerry Seinfeld Joker now. In the model, oil lag 2, which is a variable, is significant since its p-value is 0.00001. Does this variable mean, does it contain significant information? Does this variable contain significant information? So this is a multiple regression model. Multiple regression models have multiple variables. What does it mean? I'm not going to write out this answer. You have to listen in. You have to listen into this answer. So we're talking about this one right here. And what does it mean when something is significant in the multiple regression, Mary? What does it mean? So we have to be very specific about what this p-value here means in a multiple model. What does this mean? It brings new information, exactly. So the variable itself does not necessarily contain significant information. That's great, nice job there, Campbell, too. And we're on the ultra lag today. I figured it out. It's a workaround. It works. So hey, we got things working on ultra low lag today. So it brings with it new information. This does not mean that by itself it contains significant information. So by itself, it may or may not contain significant information. We do not know the simple world. But in the model with all the variables, it brings with it new information. So what being significant tells us in the multiple world is that with the inclusion of the other variables, this variable brings with it new information that the other variables are not accounting for, and thus it is statistically significant. This does not let us know in the simple world if it is statistically significant. We do not know if this variable by itself carries enough importance that it'd be significant by itself. In the multiple model, IMDb, it's Internet Movie Database. IBM lag 2 is not significant since its p-value is 0.633. Does this mean that this variable contains no significant information? So once again, this is a multiple regression. And so what does this mean? It just means the opposite of it bringing new information. If this is its p-value, well, then in the multiple world, it does not bring with it new information. So, thank you so much, Ryan. Did some fun joking around at the start of this. So thank you, Ryan. Appreciate it. It's fun. I've got my green juice, healthy green juice. I can drink water and green juice. Amazing day. Bold House and Naked drinks, those are awesome. It's where the good quality juice, that's where I used to drink, all the, Capri Suns and stuff, but you need good juice is what you need. We had fun this morning. This is her eyeshadow. One of her palettes. So we had fun this morning, and she said I looked great. So, and we've done Harley and Joker before, and she's got so we've both dressed up as Harley and Joker. And so I'm sure in the future, except I might not have the long hair. Long hair will be going soon. Long hair goodbye. And then I won't have the hair to be the Joker. It sounds like a stage Joker. Right? There's the Joker right there. Like, we'll just do a Joaquin Phoenix Joker right there. But he has the diamonds in his eyes. Really glad he did a great portrayal. Talk about the Joaquin Phoenix Joker all class today. Really did a very, very theatrical, very real life performance, very believable performance, as did Heath Ledger. And so this variable right here, going back to the topic of the day, topic du jour, is telling us that it does not bring with it new information that's not accounted for by the other variables already in the model. So this right here, we do not have new information already accounted for by bringing this in by itself. What up, Charlie? Good to see you here. This variable might have information by itself. So more Joker. So what else do we have? What other questions? More questions. 320 has questions. Does 201 have questions? 474. What up, Tyler? Good to see you. Thank you, Tyler, very much. Someone else said they were dressed up as the Joker. I've got the Joker pants and everything, too. Got all the stuff. 1G on assignment 7. Let's take a look at 1G. BS320, you got it. So let's take a look at 1G. And I'm going to put timestamps on all the videos. Got a little behind this week. Got to make some videos. Let's see right here. What does 1G say? 1G says, report a 95% confidence interval for the coefficient of average temp. Explain why this, as well as the p-value, implies that average temp is not significant in the multiple regression. Let's go ahead and make this one. Let's make the multiple regression. So let's grab this right here. It's probably going to help me put better timestamps. And it's gone. All right. Joker quotes all day long. I'm probably not teaching it. Who knows? We might need another section opened up. Who knows? Who knows? I don't know. But Magic 8 Ball, my fake Magic 8 Ball. Magic 8 Ball says, looks unlikely. So, thank you, Charlie. It's a fun day. I'm glad it worked out. I was worried when I got up this morning, I couldn't find my eye makeup. Gotta have eye makeup to be the Joker. And so I couldn't find it, and I was like, oh, no. And I was really worried we wouldn't have the Joker today. But we do. We do. And so let's go here to library reg class. I should hop over to Twitch later today just for the heck of it. Do you not choose what classes you teach? It's kind of, I do choose a little bit. I get talked to about it, like in a good way. Not like I get talked to, and I'm pulling up the EX4 demand data set as we talk right now. It's just kind of, as a department, we have all different people who teach different classes. So we try to kind of make a plan. Cops, they've got plans. The business analytics department's got plans. Brian Stevens got plans. And they have to work all these plans together. You got to make a plan together. Do I look like a guy with a plan? Do I? Why so serious? Do I look like a guy with a plan? So we put everything together. I do not get the D. I don't understand. I know that why so serious. I don't get the D at the end of it. I don't know if that's a typo or anything. Well, if you get a 474 per second, oh, that's what you're saying with Ryan. There's 2 Ryans. There's so many Ryans, and there's a Brian. I'll try to let everyone know. And right now I'm teaching 4 classes. I've taught 5 classes before, right? I don't know. Maybe I should say, hey, I'll teach 5 classes. It's 3 preps. You want to know how I got these scars? Well, my father was a statistician, and I'm a statistician. So I got these scars. I'm planning a video for 320 today, or for 201 today, where I'm going to say that. Like, you want to know how to solve assignment visualization 8? My father was a statistician. He really was. My dad's a statistician. So it's true fact. True fact, not fake fact. So let's make the model right here. We're making the multiple model. Yeah, we're gonna do we'll do a video for that. I planned to do it as the Joker, and I was like, well, I'm gonna dress up as the Joker on Thursday, and I moved it back to Tuesday. So maybe other classes are moving back too, I hope. But I'll put out that video. I should get it done after this. But I was like, I haven't done anything fun intro for a while. I was like, well, I'm dressing up as the Joker. Let's just do a Joker video. Joker does visualization number 9. So definitely. Here's the multiple model. There you go. Here's the multiple model right here. There's the coefficients, everything in the multiple model right here. So with the multiple model, what do we have? We have a coefficient for average temp. We have average temp. We have a coefficient for effective average temp. We have this. Yep, this is 1G. Yep. And what we have to do for 1G is we have to look at, is average temp significant? So, well, one, in the model, is average temp significant? In the model by itself, is average temp significant? In the model by its, like, not by itself, I should say, but the variable. Is the variable average temp significant? No, it's not significant. And that means what? As we were just talking about in the multiple world, that means average temp with the other variables included in the model does not bring with it 2 words, blank information. Average temp in the multiple model does not bring with it what? It's not peeling. You can't see it, but I actually do have scars. You gotta see the scars. You want to see my scars? I'll show you. New important information. Oh, wait. Wrong camera. There's my scars. These they're pasted on. You can see where they're pasted on, but they're actual scars. So, fun stuff. Back here to the main cam. Might have been able to hear me a little bit in the microphone. 2 camera setup. Too many worlds. Too many worlds. Too many worlds. You can see the edges of it. I'd put more makeup on if I was going out in public. I'd pat some more makeup around, or maybe kind of like, I don't know, file it down or something. Who knows? But lots of fun. So it looks like I just put makeup up this way, but yeah. And I don't know. We did this one year. We went out and had a lot of fun. So it was 2 years ago. Man, it was so fun. Last year we were going to do Rick and Morty, but then I was going to be Morty and Chelsea was going to be Rick. And but we couldn't. Last year it just didn't fall on the right night. We went looking for parties, but then none existed. Hey, Brian, just hopped in. I have a question when you finish one. Sure. And what do you notice about the confidence interval for average temp? So we've kind of done 1G right here, just having a little fun and stuff. What do you notice about the confidence interval for average temp right here? What is a big key thing for this confidence interval? Because we're trying to estimate the coefficient for the model. So right now we're trying to figure out the coefficient for the model. And what do you notice about the estimate for the coefficient of the model? The coefficient of the model might be this. Because this interval right here is related. It's very sus. Well, the coefficient, remember, the coefficient is telling us how does, like, this is a very, like, not so good interpretation. But the coefficient is telling us how average temperature impacts demand. So the coefficient is telling us how does average temperature impact demand. So the coefficient, or the impact on demand, or 2 days that are otherwise equal, that differ in their average temperature by 1, the day with the higher average temperature is expected to have a demand of 63 more bikes than the day that has the lower average temperature. Very similar, but we need to make sure we say 2 days that are otherwise identical, that differ in their average temperature by 1 degree, are expected to differ in their demand. What up, Alan? By 63.309 degrees, where the day that has the higher average temperature is expected to have a higher demand. And then what do you notice is down here, the interval contains 0, telling you that this coefficient right here could maybe be 0. Everyone gets 1,000 for being here. Ryan's DLC skin. Oh, this is the pre-order skin. You had to pre-order your class to get this skin right here. And actually, my skin's turning green if you can't see. Like a little hue on my skin. So this is the pre-order bundle. It's the Ultra Edition of BAS 320 pre-order. I hate that. Pre-order stuff is not fair. Because then you don't pre-order. It's like, you never get it. $2.99 EA DLC. What skin will there be tomorrow? What skin will there be tomorrow? Where is Brian Stevens? Should start the next class with that. We need to make up some quotes. I'll start next class. I'll be like, good evening, everybody. We are tonight's entertainment. I just have one question for you. Where is Brian Stevens? Are you Brian Stevens? Are you? EA Sports. It's in the game. So what are we learning about this right here? We're just having fun, relaxing today. We see here that this is not significant, which means that the interval does contain 0. It's synonymous, as in, if it's not significant, the interval for it will contain 0. Now, don't think because something is not significant, the interval contains 0. We're only talking about for the coefficient estimate of the model. So every time you see an insignificant p-value, don't be like, okay, that means the coefficient is 0. It only relates to the coefficient estimates of the model. Now, what does this p-value mean down here? This p-value would mean we have good evidence what is not 0. So I think this is for the whole model. So this is a totally different question, not related to this homework assignment, but this p-value right here would tell us that we have good evidence that at least 2 of these things are not equal to 0. Well, one of them more specifically, because you can only see one in this. So this p-value would tell us that we have good evidence that what is not equal to 0. So for this one, this is for the whole model. So it's related to this output right here. So since this is the whole model, for the whole model, you'd want this to be greater than 0. So what for the whole model would you want to be greater than 0? For the whole model, the r squared. The r squared, we have evidence that this model explains a statistically significant portion of the variation. So we have evidence that this model is explaining the variation. Because if the r squared was 0, what would the p-value be right here? If the r squared was 0, what would the p-value be? The p-value would be what? 1,000 points, who knows? First person tell me. If the r squared was 0 and this model explained nothing, you're right. It would be very high, and it'd be as high as it can get. How high would it be? It'd be 1. Yep. Because then that model is just as good as the naive. It does no better than the naive and the naive. And what would all these coefficients be? All the coefficients would be 0, and all the p-values here would be 1. And the intercept actually might not be a 1. I mean, it would probably not be 1 because the intercept would have some value. It would be the mean of y. So the intercept would be the mean of the y values and probably would be significant, but the intercept does not mark how we make significant models. What other questions are people wondering about? We can talk about a simple and complex model. So let me do this. Okay, I'm doing a different partial f than the one you are doing. This is a different partial f than the one you are doing. Why do we use a partial f? To see if going from what to what does what. When we use a partial f, what is the point? 2D on tonight's homework, you got it. I'll do that right. Yeah, actually, you got it, Colin. So why do we use a partial f? Why in the world? How's it spelled? Wind speed. No average wind speed. What did I mistype? AVG wind speed. So close. So close. There we go. You want to not cover my whole screen? Why do we use a partial f? What is the point of a partial f? What is the point of a partial f? Any ideas? Anyone? Bueller? Cross movie references today. Bueller. What is the deal with the partial f? The partial f tells us, see if the complex, exactly. So it's like multiple variables, seeing exactly, Campbell, that's a great way of putting it. Does the complex model bring with it new information? Does the complex model, oh no, don't worry, Charlie. Basically, let me make it make sense, Charlie. We're asking which is better. We're saying, is this complex model better than the simple model? And all we're going to do, and all we need to really know is to look at the p-value. So all we need to do is take our two models here, and this is how it'll look. Our simple model here has less variables. That's why we call it simple. The simple model has in it 2 variables. Here's the 2 variables in the simple model. The complex model has in it 4 variables. So we're going to ask, Does the complex model do better than the simple model? That's all we're asking. We say we have a 2-variable model, we have a 4-variable model. Does this 4-variable model do better than the 2-variable model? So all we do is we write the code simple, comma, complex in the ANOVA, and it does the test for us. And what's the answer? The answer is very much what? Going from the simple to the complex. And this will use the word that Canva was using, that going to the complex does what here? What does going to the complex do? I've got the jacket, but it won't work with the green screen. Or I've got the vest. Going to the complex, using the complex model, brings statistically significant information that's unlikely due to random chance. So it's the p-value right here we have to look at. So it brings, hey, what's up, Nikki? Good to see you here. So it asks questions if you got them. So the going to the complex model brings with it, oh, she put a Joker card. That's a really nice Joker card. I didn't know they had that. Got the very end of my green drink here. I'm going to choke on it. Why doesn't one have a p-value? Oh, are you talking about for this? This right here, we're doing it. It's only, thank you very much, Nick. I appreciate it. We're doing it only for the, so the F ratio, the F is the statistic of how this is calculated. It's the ratio of the, basically what we observe being explained with the new model over what we would have expected via random chance. And so we're doing a ratio of the variation we see of the increase. The really complex way of saying we're just looking how well this model does. So the F ratio you would expect here is 1. If you remember when we talked about F ratios, the expected F ratio is 1 because then we would observe what we expect. The easiest way to think about F ratios is simply, it's gone. Gotta say that every time we remove something. That's the F ratio. It's the observed over the expected. And since our F ratio right here is 21, we're saying what we observed was 21 times more than what we expected for the variation being explained. It could have been something like, this is just theoretical. It could have been something like this right here. This F ratio would turn out to be 21 because what we observe, the top number, is 21 times more than what we would expect, making an F ratio of 21. Oh, Chelsea, yeah, Chelsea's been Harley Quinn. So I should find that picture of us as Joker and Harley. It's like one of my favorite pictures that we've ever taken. I don't have it here right now, but maybe I'll go find it. She's not Harley today because, yeah, she's taking care of animals today. So she goes into work as Harley Quinn. They're like, what? So she did a great job as Harley Quinn. It was a lot of fun. We did like a Nolan Harley Quinn because there's been no Harley Quinn in the Nolan verse, and I really wish there was, though. Nolan verse being the Batman movies, Batman Begins, Dark Knight, Dark Knight Rises. It's sometimes called the Nolan verse. And then you have, the Suicide Squad Joker, and then you have Joaquin Phoenix Joker, and then you of course have Mark Hamill Joker. Hey, what's up, Adam? Sweetie Brian. Nolan was so good. Yeah, Nolan did a great job. Very real world. Bane was all right. Bane was good. I mean, I just had Dark Knight. You can't beat Dark Knight. It's so good. And more white paint comes off my nose. It's makeup. But yeah, definitely, if you haven't seen Dark Knight, oh my gosh. I saw it in theaters 3 times. I took my dad to see it. I don't know if he got it. I went to see it opening night, went to see it with one of my best friends, and then went to see it with my dad. And I was like, every time. And then maybe while it was in theaters, someone sent me, Heath Ledger was awesome. Maybe someone sent me, how did they? Yeah, they did send it to me, right? One of my friends gave me a copy where someone like cam recorded it. I went to see it 3 times. I bought like 2 or 3 copies of it, like so not saying, I don't know, he found it. I didn't find it. So, but man, that movie is so good. So good. You were the Joker last year? Which Joker? Joaquin Phoenix? Or which one? When I went out as this one night, we saw Suicide Squad Joker. You think the darkness. I can't do a good Bane. You think the darkness is your ally, but you merely adopted the dark. I can't do a good. He's like, you think the darkness is your. You gotta do that, and I gotta make up all my hands. I can't do a good Bane. I don't practice it enough. You should watch Bane from Batman the Animated Series. We can get serious here. If anyone has a serious question about any of these things, we've talked over the partial F and stuff today. But you should watch Batman the Animated Series. Bane he's written as a villain who's very intelligent and very strong. So he's kind of a big threat to Batman because he's super intelligent and super strong. And so he's basically like an evil Batman, if you think of it that way. And he wears a luchador mask. Because in the he wore like a breather mask. His mask wasn't so much a luchador mask. But he's, I don't know, you gotta watch. There's a scene where Superman fights Bane, and it's so good. You look up Superman fights Bane for the animated series. It's so good because Superman's impersonating Batman. Long story there, but Superman is pretending to be Batman, and he fights Bane, and Bane just like takes him out. But of course, Superman's fine. I'll send you a picture on it. Yeah, do that. I want to see. Yeah, was it Joaquin Phoenix? Man, maybe next year I'll do Joaquin Phoenix Joker. I don't know. I love. Like, let me see. If you send it out on Discord, I can take a look. What questions do people have? Yeah, Joaquin Phoenix. I could have done Joaquin Phoenix. It probably would have worked well with this if I had done the eyes. I don't have the right shirts and everything. 2D finishing. Yeah. Oh shoot. Let's go grab that. You said that, Colin, and I forgot. I got mesmerized by. What is the standard error for the coefficient? Yeah. So what does... Oh, thank you, Colin. You're the best. Positivity. That's what we echo right here. The Joaquin Phoenix Joker. I thought it was good. I give it like a 7.5. Just saw it. Thought it was very good. I like Dark Knight better. So what is the standard error of the coefficient of IBM lag 2? Closing price of IBM private blah, blah, blah. And what does the number tell us? The VIF is 17. What does the value of the variance inflation mean? Anytime you see variance inflation, what should you instantly think of? We don't want to memorize definitions. We want to know what these things mean. What can you do to variance inflation to give it more context? What do we do to variance inflation to give it more context? We want to take... Because variance we don't really use. What can we do to variance to give variance more context? Well, that's how we get it. That's the function. That's correct. Yep. So we can get the variance inflation factors for this. But what does variance inflation factor mean? What does the variance inflation factor mean? Yep. Charlie, you're right. You got it. We can do a problem like that, Charlie, if you want here after this. We could do one of those problems. Exactly, Campbell, you're right. So you take the variance inflation factor and you square root it. Wow, Luigi. So variance inflation factor square rooted is the standard error inflation factor. So, you got it right. It degrades the precision of accuracy in the predictors. Yeah, exactly. It makes them more uncertain. That's a great way of putting it, Colin, right there. 100 points, everybody. Campbell, Charlie, Colin. It puts more uncertainty. Standard error is uncertainty. We always call standard error uncertainty in this class. And so it's going to inflate your uncertainties. And these are the uncertainties in the coefficients. So it's going to inflate these uncertainties in the coefficients. This is a bad thing. So the precision is like, you think about an interval, Charlie, so we're talking about precision for confidence intervals, a very precise intervals like this. So it's going to degrade the precision, making it larger, because think about this. How many standard errors do we go out for a 95% confidence interval? So Charlie, you're hearing some overlap between the classes. Let's code for a problem that uses, oh, Charlie, you are the man. When you find out how easy it is to code those, I'll show you something and you'll be like, no way. No way. If you have your estimate right here, you go out 2 standard errors, 95% confidence interval, exactly. So if you go out plus 2 standard errors, and you go out minus 2 standard errors, you get a 95% confidence interval. So in excellent work right there, Colin. And then what happens if we increase the standard error? We get a rainbow interval here. What happens if we increase the standard error? If you increase the standard error, your confidence interval will get wider. If the standard error gets larger, your confidence interval gets wider, and that's what Colin's saying by it. It's going to make your confidence intervals wider. So about how much wider are these confidence intervals? Well, all we need to do is take the square root of 17, and I'll let people find that, but that's basically the answer. I try not to show as many answers, but we just do that right there, and there's the answer for about how much wider the intervals are. So the intervals are about that much. Well, would that be right? Yes, it would be, because we'd be timesing the standard error by that. That's about how much they're inflated. So we have about, it's a little bit more than 4 times the uncertainty. So you're about 4 times as more uncertain. Does it sound good to be 4 times as much uncertain? Like your interval might have been this, and you're going to be 4 times wider. I can barely show that on the screen. Like if I say like this is your interval and then you're 4 times more uncertain. So that's not good. You're going to get a much more uncertain interval. So this leads to possibly what? If 0 is one of the numbers that could be in your interval, maybe 0's here. And if you make your interval wider, then the coefficient could be 0. So this is really going to hurt the p-values right here. The p-values are going to go higher because you have more uncertainty, less room to be significant. Let's not blow things out of proportion. Let's not blow things out of proportion. Want to see a magic trick? He's gone. Earlier in class, I thought I broke the camera. I thought the camera died because I hit this button. And I was like, oh my God, the camera just broke. And I was so freaked out. I was like, oh gosh. I was like, that's it. I was even starting to set up another camera. I was literally taking my backup camera and setting it up and being like, well, I guess I'm going to have to get the backup camera set up. Gotta know how to do things on the fly. Gotta be quick. Gotta go fast. So I know, right? You should watch the 474 recording. I hit it at the very start of class. And I was like, well, I'm going to be fixing this for a moment here. Everyone in class was like, what was going on? Because they were like, is this real life? Because I appeared as the Joker and then I hit the wrong button. I hit fade to black. When I walked back over here, it was blinking. I'm glad these buttons blink or else I would not have known. I would have seriously set up the other camera and just went with it. So what's really cool, check this out, Charlie. We're going to do a problem here. And let's go grab a problem that has a confidence interval. And we'll show how easy these are to solve with code. We'll do it 2 ways. So we're going to pull a chapter 14 confidence interval homework question. So let's do a chapter 14 homework question here. Preview. Okay, so let's do a chapter 14 homework with code. So this question right here. Let's do this. We'll do this one. Let's do it. And ask questions 320 or 474 if you have them. Yeah, 2A, you got it. We'll do that one next here. Can you repeat what you said about 4? Did you mean 4 standard errors? Well, remember, here, let me hop back. We'll do this in a moment here. So let me pull back up the Word doc. So the question is, what does the value of the VIF mean? So what does the value of the VIF mean? The VIF is about how much we've increased the uncertainty, but remember to square root it, and then that becomes the standard error. So the standard error is our uncertainty, but we have to take the square root of the VIF. Does that make sense, Colin? To talk about how much we have increased our uncertainty or how much we have degraded our uncertainty in the estimates of the coefficient, we have to square root the variance inflation because the variance inflation is the square of the standard error. Does that make sense right here? How we have to turn it back into this? And then this will be the amount by which we've increased our uncertainty and, in the variable. Yep. I will do 2A right here. 2A, fit a model predicting AA from all the other variables. Run the check regression, see if the assumptions are met. Report the R-square adjusted and comment where this model may be useful. So this is the EX4 stocks data frame. So let's go see that. We gotta go here, load data EX4. I wish I was an hour in the future. That way I'd be getting up at like 8 each morning to teach at 9. Oh, it'd be so good. Next semester, my schedule's pretty good. Next semester, I'm not getting up so early. There's the dot. I forgot that comma yesterday, I think. No AA found? No AA. Oh, bike. I was like, that is in there. There we go. Stocks. So we have here the model. And let's just do the check regression. Do we need to run an output on this? And here we go. You know what? How's this look? Let's look at this check regression. How's this look? Tiny Joker Brian. How's it look now? How does this look? I think this is the longest I've worn the Joker makeup for. How does this look? We should take the p-values to start, in truth. Equal spread looks good. Linearity looks good. This looks normal right here. Yep. So you see, this is the normal curve, and then this is the QQ plot. So if you remember, Charlie, we did the QQ plots for normality, and this follows the straight line, so it's mostly normal. And the p-values are probably pretty high for all these. That fails, but you know, none of them are really bad. These are the individual variables. There's some issues with linearity on some of the x's. Like this has an issue. Any p-value below 0.05 has an issue. That barely has an issue. That has an issue. So some of those, it can't do the p-value for the overall model. The equal spread passes and the normality passes. So the only issues we see are for some of the individual x's seem to have issues with the individual x's have linearity problems. Good to see you here, Miles. So we have some issues with some of the individual x's having problems with linearity. So some of the individual x's have problems with linearity. I'd mention them. I think it does say to talk about that. See where these I would mention if the assumptions hold up. Since you've run it, I would mention I would do a little short write up and talk about there's issues because some of the p-values for linearity are below 0.05. And looking at the overall plot, it doesn't look like the model as itself does have issues because the overall plot is this plot right here. And then the next question is, we need to look at the summary of the model to see if it's useful. So, whoa, look at that. What do you notice right here? What do you notice immediately? And this is a 201 interpretation, Charlie. What do you notice about this? And you can just say the model for the x's. So we're predicting the Alcoa stock. What do you notice right here? And this is kind of why you can track stocks with other stocks. I mean, it makes sense. It's like stock market goes up, stocks go down. They follow each other. So what does this mean, though? Yeah, exactly. And then 80.07% of the variation in the Alcoa stock is explained by this model containing the other stocks. So this is very useful. This is a very, at least in terms of R squared right here, 80% of the variation. And then if you use this model, you will typically miss the price of the Alcoa stock. Your prediction will typically be off by about 84 cents. The typical miss this model makes when predicting Alcoa stock is about 84 cents. The multiple R squared suggests that 80.07% of the variation of the Alcoa stock is explained by the variables in the model. And then the 75.52 is our R squared adjusted, which means after we adjust for the variables in the model explains about this much variation. It's after we adjust. It's a penalty to R squared. So, I wouldn't really interpret it. It's just a better look at R squared with when we penalize ourselves for the variables in the model. And so pretty good model. Two things to look at for practical significance right here are this and this. Interpretation of your RMSE and your multiple R squared are your practical interpretations. And then this right here is a check to make sure you haven't put too many variables. You don't want this to be about 10% smaller than your R squared. And does that make sense right here, Ryan? Does that help out with this question? Do you have some good stuff to write right there? And remember that practical significance relates to this and to this. And you can mention that a little bit. And of course, it's very statistically significant. Nice job, Ryan, right there. So this is super duper duper statistically significant. The model's ridiculously significant. You see some of the x's are not significant, but like that, what does that mean? You see this lag 2, where's it at? It's on here somewhere. There it is. This variable is significant. Cool, Colin. Have a great day, man. Hopefully, you were telling me about all the interviews last time and everything. Hopefully they went well, and I don't know if I heard how they finally went, but great job, man. Good luck. So we see here oil lag 2. Oil lag 2 is significant, which means it brings with it new information. We see right here global Dow lag is not significant, which means in this model it does not bring with it new information. It might be significant by itself, and we could check that. We just go here and we make the simple model, and it is super significant by itself. So this variable by itself is significant, but in the multiple world, it does not bring with it new information. You don't know if something is or is not significant by itself till you check. So this model is significant this variable is significant by itself, but in the multiple model, it does not bring with it new information that the other variables are not accounted for. And here we go. What do you think? Everybody was depraved as you are. It's like Batman talks like the Joker. Everyone, when Batman Begins came out, people were laughing at Christian Bale's voice because he's like, where were the other drugs going? Like, pray to me. That's my favorite line in Batman Begins. He's like, oh, swear to me. The line is swear to me. He's holding up the crooked cop, and he's got him upside down. I think he's holding him by the tie upside down. He's like, I swear to God. And he's like, swear to me. It's such a good line. Oh, man. Or when the guy says, where are you? And he just says, here. It's like, guy screams, "Where are you?" And he just is here, and he like envelops him in his cloak. Oh man, Batman Begins is underrated. He fights Ra's al Ghul. He fights Liam Neeson. Liam Neeson is Ra's al Ghul or Ra's al Ghul. Did they say Ra's or Ra's in it? I think they said Ra's. I can't remember. I think it's Ra's al Ghul, but they say Ra's. Great movies, great stuff. Good to have everyone here. What questions are we doing? We can hop over to the 201 stuff. I've got that open in the background. We're talking about some confidence rolls and stuff. Joker paint everywhere. So let's explain what this interval means. I'll do one more fun than this. What's up, Matthew? Glad you're enjoying it. Okay, let's do this problem right here. So we're gonna show some power of coding right here, why coding is awesome. Because what we need to do in this problem for 201 is we need to first identify notation. So here's what we're gonna do is we're gonna take this interval right here, and we're gonna go grab it, put it right here. It's gone. It's back. So here is the interval. Well, not the interval yet. We're going to go solve it. And let's do this. So we need to identify notation. 316 is what? Someone help me out. Have some fun here. Help me out. Identify one of these numbers. 316, 37, and we got 95. We got all these things we need to identify. What do we have right here? Someone help me out with one of these. I need at least one of these answered. It says a nutrition laboratory tests 50 reduced sodium hot dogs, finding that the mean sodium content is 316. Oh, there we go. That's the mean, and that'll be X bar. Why is this X bar and not mu? It's because it's from a sample. So it's from a sample. And then this will be S, and it's S because it's from a sample. The difference between X bar and mu, I can't write mu today, is X bar is from a sample, mu is from the population. The difference between S and sigma is one is for population, which is sigma, and then S is for sample. So make sure you know those differences between your samples. We'll write them above. These are samples, and these are population. And this is the mean, and this is the standard deviation. So just knowing kind of this right here, that these are population parameters, and the other ones are sample statistics. How do I know these are sample statistics? Because all of this information came from a, wait for it, sample, a sample size of 50. So all these came from a sample size right here, and this gives us our confidence level. So now that we've identified everything we need, we just need a formula. The formula we're going to use, I guess we call that y bar in our class. Bar just means the mean of the variable. Y bar plus or minus the t with n minus 1 degrees of freedom, and S over square root of n. So right here we have the formula we are using. And yeah, now we just need to find t. So this is what Charlie was talking about here. What's up, Joe? Hey, Cincinnati Stats, so good to see you. You want to see a magic trick? Cincinnati Stats. My father was a statistician. He really was. My dad is a statistician. Do you want to see a magic trick? I'm going to solve this confidence interval. We need to find a t-statistic. Where is a t-statistic? Well, we don't use t-tables in our class. Do you use t-tables in your class? A lot of people use t-tables. Nothing wrong with t-tables. Nothing wrong. Sounds like I'm saying something's wrong with the t-table when I say it. The more I say nothing's wrong with the t-table, the more someone's going to be like, Mr. Joker, why do you hate t-tables? I grew up using t-tables back in the the 90s, early 2000s. I was using t-tables. A t-table just has all the values here that we could find. And then they used to say to me, well, you can't use the applet. Well, guess what? I've got the applet on my phone. It's Matt Bogner of University Cincinnati. More shout outs to school right here. But Matt Bogner, which apparently I deleted his app. I guess I was running out of space. But he wrote this probability distribution applet thing, which you probably can't see. But you can bring all the applets up on your phone, which is really awesome. Phone's got makeup all over it. So StatCrunch oh yeah, StatCrunch, because you're probably using Pearson too, right? StatCrunch has t-tables? We should use StatCrunch maybe. So we go right here, and here's what Charlie was talking about. Charlie, let's show off some knowledge right here. Charlie, boom, Cincinnati Stats, let's show it how it's done. Charlie, what are the degrees of freedom for this problem? We're identifying the degrees of freedom, Charlie. So what are the degrees of freedom? Let's here we go. What are the degrees of freedom for this problem? 49, nice job. For a one sample t, it's n minus 1. For the one sample t, it's n minus 1. So just remember that. Kind of put in your head, one sample t, n minus 1. There'll be other times we use degrees of freedom. What do the degrees of freedom tell us? They tell us which t distribution we are using. One of my favorite things is Mr. T comes in here and he says, "I'll pay the fool." I'm not dressed as Mr. T today. I wouldn't do that anyways. But he comes in here and he slams down and goes, "I'll pay the fool." And then Mr. T gives it more freedom to be normal. It doesn't exactly, well, it eventually does become normal with enough degrees of freedom, and it would require infinite degrees of freedom. So the t distribution approximates the normal, the more degrees of freedom it gets. And I said one day a statistician would come in here and get mad at me for saying this, but the t is basically the normal. Big star on that. Big star. The two sample t-test is, and Cincinnati Stats, correct me if I'm wrong on this, because we do the assumption of unequal variances. And if you assume equal variances, the two sample t and the paired t are n minus 2. Cincinnati Stats, I just don't do that one. We do the assumption of unequal variances. My dad would be mad at me. The two sample t-test, we use the complicated formula for it, and we don't figure out the degrees of freedom by hand. No one's going to do that. So the two sample t-test, there is one with n minus 2, and that's going to be your equal variance, and the unequal variance uses a more complicated formula. I can show you that formula here real quick. Did we lose Cincinnati Stats? No, hopefully not. Wait, I remember from stats in high school it was n minus 2. I thought, yeah, and there's so two sample t-test, degrees of freedom. There's two different formulas for it. So here, we'll hop over here. And they're probably talking about it right here. So the degrees of freedom, I just never solved this by hand. So there's different formulas for it. Here's the degrees of freedom. There we go. Just depends on if you're doing the equal variances or unequal variances. It's an assumption used in it. Have to run, take care. Oh, we lost them. So we will use this complicated one right here. Good seeing you, Cincinnati Stats. Thanks for swinging by. So we're going to use the more complicated one, Charlie. Does that make sense? There is the assumption of equal variances, and that will use a different one right here. So it just depends on which test you are using. Hi, statistician come by. Oh, no. So, yeah. And what the big thing is when you do it in statistical software, when you bring up your statistical software right here, in your statistical software, you have the option of how to run it. When you do your test and you go over here and you do gender and you do like people's heights, you can actually choose right here how you're running your t-test. So you can go to your t-test, you can compare means, you can do different types of tests right here. It all depends. And you see assuming unequal variances. So we are doing the unequal variances. I got it reversed. So we're doing the unequal variance assumption right here. If you assume equal variances, which I think, so here we go. Assuming equal variances right here. So the sample size is 730. Does that make sense, Charlie? There's 730 sample size. So assuming equal variances, which I always get this reversed. Assuming equal variances, the degrees of freedom right here are 728. Does this make sense right here, Charlie, that the degrees of freedom are 728, just like you said, two sample t, it's going to be 728. Does that make perfect sense right there? Like you just said, you got it. And then down here, when you do the unequal variances, the degrees of freedom are no longer 728. The highest it can be is 728. Like theoretically, the highest it can be is 728. You'll get n minus 2 as the highest possible degrees of freedom for the unequal variances. And so just depends on which t-test you're doing. So, and what does the t-test tell? What does the t degrees of freedom tell us? The degrees of freedom for the t tells us what? Yeah, exactly. It's basically 728. And you could basically, like, the t statistic is basically the z. I was hoping for Cincinnati Stats. Now we're going to have a stats wars right here. So it's basically 728. That's basically n minus 2. The issues you run into, it'll be vastly different. The degrees of freedom for the two sample t. So two sample t degrees of freedom calculator. So I'll show you how this works. Oh, someone else has another calculator online. Where's Charlie's? Oh my gosh. Charlie's is not the top hit anymore. Oh, because I'm in Texas. No way. I might actually have to go to our site. I'll have to tell Charlie here in Texas we don't go to his degrees of freedom calculator. Makes sense. Here it is. So what happens is if your sample sizes and your standard deviations are equal, this will be 198 degrees of freedom. So this is 198, but as soon as your sample sizes or your degrees of freedom get, or your standard deviations get different, you start to see different degrees of freedom. Oh, so this is, we changed, we're talking more broad topics right now, Charlie. This is no longer a one sample t-test. We're just kind of talking if we have two samples and do a two sample t-test, where you have like males and females, or you have Florida, UT, things like that, or Cincinnati, Tennessee. So this is just talking about the two sample for a moment right here. And so if you don't have equals of these, you won't get the same. We will do this later on, and you don't have to do this by hand. We let you use the calculators and stuff like for this. So you can use the calculator here and just put in your sample sizes, put in your standard deviations, and it'll tell you the degrees of freedom. Now, what is the whole point of knowing the degrees of freedom? Knowing the degrees of freedom will tell you the what you're using. The whole point of knowing the degrees of freedom is to take this and then bring it over to where? Like the whole point of knowing your degrees of freedom tells you the blank you're using, especially for this sort of test. It'll tell you the distribution you're using, and specifically we're using a what type of distribution. It's all right, don't worry. We're using a T. And so the whole point of this is every T looks different. Every T distribution looks different depending on the degrees of freedom. Yep. So every T distribution is going to look different depending on the degrees of freedom. So if we have like 1 degree of freedom, this is where Mr. T says, I'll pay the fool, smashes it down. 2 degrees of freedom, 3, 4, 5, 6. You see, it starts to rise up and it becomes basically the normal. So the more degrees of freedom you have, the more normal it is. And so this right here is going to be with more and more degrees of freedom, it becomes more and more normal. So does that make sense right here? What we have is we have more and more degrees of freedom. It's more and more normal. And so the T, the reason the T exists, so the bigger the degrees of freedom, the sample, so the bigger the sample, the more the degrees of freedom, thus more normal. Exactly. What the T is it's a correction for smaller sample sizes where you might underestimate the variation in the data. It's it kind of, I mean, kind of. It approaches the normal distribution. So we have right here that there's smaller differences, that you basically have the normal, and so it's still gonna, yep. And we use the central limit theorem here to say that this distribution will be nearly normal given a large enough sample size dependent on the shape of the distribution. And does the my Pearson question really work on that really well? So we have the 50 hot dogs. Let's go back to our question right here. And we have the sample size, we have the sample mean, we have the standard deviation, and then we just need to fill this out. And I think the T is like 1.9, no, 2.04 maybe. I say the T is 2.04. So we have 49 degrees of freedom. 2.01, 2.01. So we're going to put it right here, 2.01. And then we put in the standard deviation. And we put in the sample size. Standard deviation is 37. Sample size, wait a minute. Did that yesterday. And then we go right here and put in the mean of 316. And that's got it. Yeah, sure, Ryan, let's do that next here. And so that's how you solve this one right here. Once you solve this, Charlie, you're done. So you can also put this in your calculator. If you have a TI calculator, it's the one sample t-test. And the one sample t-test will solve this instantaneously on the TI calculator, and you can use that on the test. So does this make sense here, Charlie? How to plug these in? How to get these answers? Hopefully, nice. Awesome work. Let's go talk about 2B. 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 Where'd it go? As a whole, stock and commodity prices are often strongly correlated with each other, so there is a large amount of redundant information. Calculate the cutoff of a large VIF. So let's talk about 2B here. And how do we calculate large VIF cutoff? Well, we use the VIF formula. So large VIFs. So a large VIF is when it goes beyond our cutoff, and our cutoff is going to be 1 over 1 minus r squared. So what we need to do is we need to take the r squared for the model and see what a large cutoff would be. I'm going to do a different model right here, but similar. So let's go and take this model right here. We'll take the complex model. What would be a large cutoff for this model? And this model doesn't do so well. This model only explains 40% of the variation. So what would we have to do to find the large cutoff for this model? And the reason, if Cincinnati Stats is still wondering, is because if you look at the literature, it says a large VIF is 5 or 10. And so it's like, when is it large? 5? When is it large? 10. This one's going to have a rather small cutoff because we don't have a very high amount of r squared. We don't have a lot of variation explained, so we don't want our x's to have a lot of overlap. The VIF stands for kind of the uncertainty increase for our variables depending on the amount of overlap we have within our x variables. The more our x variables overlap in what they do, i.e. multicollinearity, then the more uncertainty we have, and we don't want that with small sample sizes especially. So what would we do right here with this number? This number right here will get taken and plugged right into the right Word document. We'll take it and put it right here. Now, this is not the answer to your question, but using this formula, we can calculate the high VIF cutoff. So if we see VIFs larger than this amount right here, whatever this solves to, which is going to be like, it's going to be like 1.66, I think. So if we get a VIF larger than 1.66, that means we have large variance inflation, which we could check for. We could see if there's high variance inflation right here. With the complex model, is there high variance inflation? And the answer is there's no complex. Oh, yeah, there's large variance inflation. Like, this is even by general standards, even by the usual 5 or 10, which is always like, is it 5, is it 10? There's an insane amount of variance inflation with this model because average temp and effective average temperature are basically the same variable. We can also see this, it's mainly coming from those two variables having the same information. You can see this in the pairs plot right here when you look at it to see the overlap between the x variables. The overlap between the x variables is average temp and effective average temp. Lot of the same variation right here. It's basically these two variables are the same variable. Is this making sense here, Ryan? What's going on? That these two variables really have a lot of overlap in what they explain, and thus they don't bring with them new information. They bring redundant information. So that's what we're seeing there in the high VIF is that, and you can see it, this is collinearity because it's just the two variables, but we're looking at it more in the multivariate sense that how is average temp explained by all other variables? Hey, Ryan, oh, that was from the r squared of the model. Yep. Great question right there, Miles. So the r squared of the model. So use the r squared of, oh, well, it's 0.3881. Was that the complex model? So, and I'll show that again. So whatever you get right here should be the r squared of the model. I'm using a different model, though. So don't use this number. So how would we come in on multicollinearity? So the multicollinearity shows up in the variance inflation factors. So, and this is the number I'm using right here. That's the number you should use for it. Did I use summary M? Oh, this is a totally different this is a totally different model. It was this model right here. It did have 0.40. Just coincidence that the other model I accidentally clicked had 3.88. So this is where I got the 0.40 from. I was like, I remember it being that. I don't remember being 3.38. So that's where we're getting to calculate the large variance inflation cutoff. How would we comment about the multicollinearity? If you're commenting about multicollinearity, you're commenting about the variance inflation factors. And right now, it looks like average temp, effective average temp have a lot of redundant information with the other x variables in the model. Average humidity and average wind speed do not have redundant information or very little to none. The smallest variance inflation factor you could get is 1, because if your r squared right here was 0, then that would mean that your x has completely unique information in it, not redundant with the other variables. That doesn't mean that your x is significant. It just means that it has no redundant information because the r squared is how is your variable explained by the other variables. And specifically when we do multicollinearity, we're using r squared sub I. And for the high cutoff, it's the same formula, but we use the R squared of the model. I'm just afraid Cincinnati Stats is watching and be like, you forgot that I on the variance inflation factor. So this is the one for the cutoff. For the high VIF, that's the R squared of the model. And this one up here is for variance inflation factor of the ith variable. So you use the R squared sub I, and definitely some theory questions on what is R squared sub I. Does everyone understand what R squared sub I is? Does anyone know what R squared sub I is? It's how is the blank what explained by the other blanks. R squared sub I is the percent of variation in the ith x explained by the other x's. So we're asking, that's how we're seeing redundant information. How is your x variable, your ith x, explained by the other x's in the model? That's your R squared sub I. And so the I stands for the ith x. And then we calculate the high cutoff by looking at the model itself and looking at basically calculating, well, given what we're doing with y, let's look at a cutoff here for how much we want to say for what would redundant information be. So it's kind of a fluid cutoff that will change depending on what we're working with. What other questions are there? It's almost the end of office hours. Cincinnati Stats came by. It's a great day. It's too bad Easy Escape B-Scape came by one day. At the start of the semester, B-Scape came by. Might try to film portions of my video between this. Well, I think that's the end of office hours. We're going to finish up here and answer some emails. Got one more class today. Could you kind of talked about this earlier, but if we do the ANOVA test and determine it is statistically significant, does that mean we can drop the other roles in the... Oh, so remember, the ANOVA test is when we look at the ANOVA, it's asking, should we go from the simple to the complex? So when you look at from the simple to the complex, statistical significance means that it brings with it new information. So when we ask, do we go from the simple to the complex, do the new variables in the complex bring with them additional information right here? Do the new variables in the complex bring with them new information right here, Campbell? Do these variables in the complex bring with them new information? So should we drop them? They do bring with them new information, so should we drop them? Should we drop them from this model? They bring with them new information. That's what the p-value there means. It means they bring with them new information. So we should not, boom, you got it right there. Yes, great job. That's exactly. So yep, you know what it means, that this p-value means that going to the complex brings new information from the simple. So since it brings with it new information, we should include these variables. You got it, Campbell. Great job. Man, I love those insightful questions. Campbell, you get the 2,000 points a week right there. So I've totally messed up the point system. But no, I really like that insightful question right there, asking and making sure you understand it, because that's what we need to do. Good vibes today, big vibes. Everyone gets 1,000 points for being here. I think that's got it. We'll do our cool outro today. I haven't listened to the cool jamming outro. If you have questions, let me know. You're welcome, Miles. Really glad it helped out. See everybody. Good luck. Email me questions if you got it. I'll be teaching here in a little bit. Last year, my friend was in your class and you were going, I know, right? I need to work on the point system. It always goes crazy. Anyways, I'll see everybody later. See you soon in class if you got 320. Bye!
Hey Brian, what's up?
Hey, Adam.
Oh, what's this?
Adam, what are you doing? Adam!
No!